Yeah. Now it is removed. Now it is again coming.
Okay.
Again it is coming. Now it is not there. Coming, sir.
Coming.
Now it is not there.
Is it fine now? Is it fine? Is it fine? Disturbance are there? Is it
Is
fine
it
now?
fine now?
No, sir. The disturbance is there actually. Yeah. Now it is not there. Now again it is coming.
Is it there now?
Little bit it has improved. Little bit. Again the sound is more.
Now?
It is coming. Now it is not there. Now it is not there. Yes, it is clear now.
Okay, okay. Okay, it is clear, right?
Yeah, it is clear now.
Okay. So, hello everyone, I am Himanshu. So, for today tutorial, I will be solving some problems related to the fundamentals of heat convection problems. So, I will be solving some problems related to the average heat transfer coefficient, which we saw last week as well. And then I will move to some problems related to Nusselt number, and then in the finally I will solve some problems related to the Reynolds Colburn Chilburn analogy, and there we will be finding drag coefficient and Nusselt number, heat transfer coefficient, and finally we will find the heat transfer. So let's start with the first question. So the first question is true and false type of question. So the first statement says that conduction and convection are similar in that both mechanisms requires the presence of material medium, but they are different in that convection requires presence of fluid motion. So is it correct? this statement is correct because even though the conduction can occur in both uh, fluid medium, let's say, this is my beaker and this is my fluid. This is my temperature T1 and temperature T2. So in this process, there will be a heat transfer due to conduction. So conduction always requires that the material medium should be stationary. But if there is a movement of fluid parcel in some random direction with some random velocity, then there will be a heat transfer due to the convection process. So convection process need a presence of a fluid motion. Even though there is a fluid, conduction can happen. Only the certain reason is the fluid should be at rest, or the fluid parcels should not be moved around in a local position. So the first statement is correct. The second statement is the heat transfer through a solid is always by conduction, since the molecule of a solid remains a relatively fixed position. Heat transfer through a liquid and gas, however, is pure convection only. And the magnitude of heat transfer does not depend on the rate of bulk fluid motion.
I think this is false.
Yeah, because as I said, the heat transfer in the liquid or gas can be happen due to conduction, and provided that the liquid and gas are stationary. So only if the fluid are having some definite movement, or there is a fluid parcel or bulk fluid which is moving, only then there will be a heat convection. So only the first statement is correct here. So let's move to the next question. So in the next question, again it's true and false. First question says that for the case of a fluid flow over a flat plate, the region of a flow above the plate bounded by sigma delta, in which the effect of the viscous shearing force caused by fluid viscosity are felt is called velocity boundary layer. The boundary layer thickness is typically defined as the distance y from the surface at which u is 0.99 v, where v is the free stream velocity. So is this correct?
So it is correct.
So this is a correct statement because usually we define a hydrodynamic boundary layer where the distance of the normal distance of the hydrodynamic boundary layer, which is a boundary layer thickness defined by the delta, and this distance is up to where the free stream velocity v, where the velocity of a fluid parcel is approximately equal to the free stream velocity. And to be more specific, we usually take the velocity of a fluid parcel at the boundary layer is 0.99 of a free stream velocity v. Similarly, for the flow region over the surface, in which the temperature variation in the direction normal to the surface is significant, is the thermal boundary layer. The thickness of a thermal boundary layer, del T at any location along the surface, is defined as the distance from the surface at which temperature difference T minus Ts equals 0.99 T infinity minus Ts. So here the free stream temperature is T infinity and plate temperature, let's say, is Ts. So is it a correct statement? So the first statement is correct. So second statement.
Second statement is also correct.
Yeah, so just like a hydrodynamic boundary layer, we also we define a thermal boundary layer, and the criteria is almost same, that the temperature difference That means the temperature of a wall with and the temperature at a fluid parcel should be approximately equal to the free stream temperature difference. And to be more specific, it is 0.99 T minus Ts. So let's move to the next question here. So in the next question,
Actually, in that when you have written this, I think there should be T infinity.
oh sorry, yeah, here it is T infinity. Yes.
Okay.
Yeah. So let's start with the numerical question. So in this question, we have to use the previous concepts that we have discussed in the previous class to average the heat transfer coefficient. So the question is the water flows at a velocity u infinity, which is 1 meter per second. Over the
I'm sorry to interrupt you. I just want to clarify that last video of the last week video, that
Yeah.
link was provided on that NPTEL site that I have subscribed. But that video was different than what you taught last time. The video is different.
Okay. Is it a previous week video?
The last week video is not there. I think that is different.
I mean, is it a previous week like 4, 3, 2 like that?
No, last week only.
Okay. Okay, I will check.
Yeah. Okay then.
Just give me 2 minutes and I'll go through it. For example, let's say picture 5. The plane like I think I upload the same, but anyway, I will send a link here at the end of the class, and I will again check if there is anything, any issue.
Okay, sir. Okay.
So let's start with this question. So water flows at a velocity 1 meter per second over a flat plate of length 0.6 meter. Consider two cases, one for which the water temperature is approximately 300 Kelvin and the other for an approximate water temperature of 350 Kelvin. And in the laminar and turbulent regions, experimental measurements show that the local convection coefficient are well described by. So we have given the local heat transfer coefficient for both laminar and turbulent case, and where x is in meters and c is a constant value for both 300 Kelvin and 350 Kelvin. As is evident, constancy depends on the nature of the flow as well as the water temperature because the thermal dependence of various properties of the fluid. And we need to determine the average convection coefficient. So we have a boundary layer over the flat plate. So there is a boundary layer which is laminar, and after some time it will become turbulent. So this is my laminar part and this is my turbulent part. This is x equal to 0. Let's say my x is the horizontal length of my laminar boundary layer and the length.
Excuse me, sir.
Yeah.
Sir, that we have here already assumed that both laminar and turbulent regimes will be there. But actually, this thing we can conclude only after calculating the Reynolds number, isn't it?
Yeah, so here in the question it is given that there is a turbulent boundary layer So in that case, we draw a profile of a boundary layer which is laminar and turbulent. Otherwise, we need to check from the Reynolds number that whether the boundary layer is in laminar or in turbulent region. So
Okay.
so we have a so we need to find the heat transfer coefficient. So let me list out the properties. So we have given two temperature, temperature 300 Kelvin, and let's say the density at temperature 300 Kelvin is 997 kg meter per meter cube, and the viscosity is 855 10 to the power minus 6, and at temperature 350 Kelvin we have a density of 974 kg per meter cube, and the viscosity is 365 10 to the power minus 6. Now, in the last week class, we know that whenever we need to define the average heat transfer coefficient, we need to take the integral over the length of the local heat transfer coefficient. So we already have the local heat transfer coefficient, and we just need to integrate it. Here we have given for both laminar as well as in the for both laminar and turbulent case. So we have to find this XC here, because the average heat transfer coefficient will be now so this will be my average heat transfer coefficient written in terms of heat transfer coefficient of a laminar as well as for a turbulent case. So we need to find the XC. We already know what is L. So here L is 0.6 meter. To find the XC, since we have given in the question that the boundary layer is turbulent flow, and we know that so XC is the length where the laminar boundary layer stays, and after XC the laminar boundary layer change into the turbulent boundary layer. So XC is my transition length. So beyond XC my flow is turbulent, and when X is less than XC,
I think, sir, it should be X greater than XC.
yeah, sorry. It should be laminar. So, and we know from the fluid dynamics knowledge that the critical Reynolds number where the transition happens for a flat plate is roughly equal to 510 to the power 5. For the pipe flow, the critical Reynolds number roughly is 2400, even though it is depend on many parameters, but this is the most used critical Reynolds number for pipe, and this is for the flat plate. So at temperature 300 Kelvin, we have rho and my XC will be REC mu1 rho 1 u, which is My new one is for 300 Kelvin is 855 10 to the power minus 6, and my density is 997, and velocity is given as 1 meter per second. So after solving this, I will get Xe at temperature 300 Kelvin as 0.43 meter. Now we have Xe, so we need to use the equation 1 here. So my, let's say it's Xe. My laminar locally transfer coefficient is 0.5 minus 0.5 dx minus 0.2 dx, and I can write this as it's 477, sorry, 395. Dx. So let me write in terms of number. So So when I solve this integral, I will get my average heat transfer coefficient at temperature 300 Kelvin is 1620 watt per meter square Kelvin, and I can repeat the same procedure for 350 Kelvin. So again I need to find the critical length for temperature 350 Kelvin. Mu2 rho2 u. So when I plug the values, my transition length will be 0.19 meter, and on using the same equation 1, and we have given C lam and C turbo for turbulence for 350 Kelvin also. So again we just need to integrate it, and we will get the average heat transfer coefficient, in this case 3710 watt per meter square Kelvin. So this is my average heat transfer coefficient at different temperature. So in this question we have given a local heat transfer coefficient which is separate, different for laminar and turbulent flow. We have given that the flow become turbulent in nature, and so we found the critical length, the length when above at the right side the flow become completely turbulent. And once we get the length, we can able to integrate the laminar heat transfer local heat transfer coefficient and the turbulent local heat transfer coefficient separately to get the average heat transfer coefficient. And we have done this for two different temperature, 300 Kelvin and 350 Kelvin. So at both the temperature there will be different properties of a fluid. So the density will decrease when the temperature increase. So, any doubt in this question?
No, sir.
Okay, so let's move to the next question then. So in this question, we have experimental test on a portion of the turbine blade shown indicate a heat flux to the blade of 95,000 watt per meter square. To maintain a steady state surface temperature 800 degrees Celsius, heat transfer to the blade is removed by circulating a coolant inside the blade. Determine the heat flux to the blade if its temperature is reduced to 700 degrees Celsius by increasing the coolant flow. So we have given the velocity and the temperature of a free stream, and we have given the heat flux and the surface temperature 800 degrees Celsius, and we need to find the heat flux. The surface temperature is 700 degrees Celsius, become 700. So we know that the heat flux can be given as, and therefore my heat transfer coefficient will be Ts minus T infinity. So this is my heat transfer coefficient. Now whether we have to check whether the heat transfer coefficient is changing or not, or the other properties are changing or not. So for that, let the Nusselt number will be HL by K, and I can write this as a function of X star, Reynolds number, and Prandtl number. My X star is some non-dimensional length here. Now, since there is a change in the temperature only, there will be no change in any dimension of the blade, and no change in the Reynolds number because the fluid is same, the velocity of the fluid is same, and no change in the Prandtl number. Therefore, my Nusselt number remains the same. So for the both case, my Nusselt number remains the same, and there is no change in, as I said, in the geometric property and the fluid property. My heat transfer coefficient will be same as well. So heat transfer coefficient for temperature 800 is equal to heat transfer coefficient at temperature 700, which means that, let's say my heat flux is Ts minus T infinity, and my in the second case my heat transfer will be Ts2 minus T infinity. Now I take the ratio of these two heat transfer. Now in that case, since my heat transfer coefficient are same, this will be vanished. And then I can write my Q2 and Q, my heat transfer flux is already given at 800, which is 95,000. And my T infinity is 1150. So now on solving this, my change in heat transfer due to change in temperature will be 122 122 10 to the power 3 watt per meter square. So let me revise the first part. So in the first part, it is said that we have given the heat flux and the surface temperature, and it says that if my surface temperature gets changed, what will be my change heat flux here? So we write the Nusselt number equation in terms of distance, non-dimensional distance, Reynolds number and Prandtl number. And since there is a no change in the velocity, fluid property, and as well as the geometric property, we found that the Nusselt number is same, and hence the heat transfer coefficient is same when we change the temperature. And then we take the ratio of two heat flux just to find the modified heat flux. So any doubt in this part?
But sir, in this thermal conductivity is a function of temperature. We have not considered the thermal conductivity.
Thermal?
Thermal conductivity K.
Oh, conductivity. Yeah. So yeah. So here. Yeah. So it is a function of temperature, but in this question, just for simplicity, it is given. I mean, we don't require as of now. Okay.
Because there is a considerable change of 100 degrees Celsius, and we are assuming, okay, Prandtl number, Reynolds number, we can, but K, how we can do this? That K is also constant.
So here we will assume the constant property, so we will not worry about the change in the property with temperature here. So in that case, K and K will be a constant, and we need to find whether H is changing the geometric and flow properties. So here in this case, the H remains unchanged. So yeah, so we need to. Yeah, so we will need to assume this property as for now, because otherwise if K will be the function of temperature, then since we have no data about the thermal conductivity, it is difficult to define the modified heat transfer coefficient here. So we can make this assumption that the properties are not changing with temperature here. Yeah, otherwise it is not wrong to say that the thermal conductivity, density, and the viscosity, even the heat transfer coefficient can change with the temperature. Because we don't have any data about the thermal conductivity in this question, so we can assume it as a constant. And one more reason for this thing is here the thermal conductivity K is of a fluid, which is already low. So the thermal conductivity of a fluid is in order of 10 to the power minus 3, around that order. So even if there is a change in thermal conductivity of fluid, there will be a very less change, because it doesn't matter like if you increase the temperature, suddenly the fluid started conducting the heat. It is not like that. In case of solid, there is a very huge significant change in a thermal conductivity, even if you increase the temperature by a little, like a 10 degrees Celsius or a 20 degrees Celsius. But for a fluid, especially air, which has a very poor thermal conductivity, which is where the value of thermal conductivity K is very, very less, already very, very less, like around 10 to the power minus 3 or 10 to the power minus 4. So even if you increase the temperature, it will not very much. So in that case, we can assume the thermal conductivity of a air to be a constant with respect to temperature for as of now.
But sir, here the surface temperature we are reducing. Then we cannot take only the fluid properties into consideration. I think at
Yeah,
surface temperature when we are having,
yes.
then
Again, this makes a sense because we are not changing the T infinity here. We are changing the surface temperature here. So even if we change the T infinity, there will be a very insignificant change in the thermal conductivity of gas. But here, since we are changing only the surface temperature, uh, the change in the thermal conductivity is even lower. It should be negligible.
but even sir, this will be the case with viscosity also.
No, the viscosity and density actually changes. For the liquid case, like water or the metallic flow, like mercury, if you increase the temperature, there will be a significant change in the properties of a fluid. But for a gas, it will be a bit less. But yeah, when we compare with thermal conductivity, the change in the density, even in the gas, should be a bit higher because it will result into a buoyancy force and that will lead to a free convection. So yeah, density and viscosity will change a bit when we change the temperature of a gas, but not a thermal conductivity and even the specific heat, I think.
But in this question, then I think every property we have to presume is to be constant,
Yeah.
because
So,
if it is a change, then we cannot calculate the change.
so basically, we need to consider if there is a change of a fluid temperature. Like in the previous question, it is given that the fluid, there is a change in the fluid temperature, 300 to 300 Kelvin, and therefore there was a change in the fluid properties. Here, the fluid temperature remains constant at 1150, and only there is a change in the surface temperature. So we can neglect the change in the thermal conductivity of a gas because we are talking about thermal conductivity of a gas, not a solid. So in that case, there is a very negligible change, and that change is only occur near this surface only. Otherwise, the thermal conductivity everywhere around the body is remain unchanged. Only near the vicinity of this surface, there might be some negligible change in the thermal conductivity of a gas, and remaining everywhere, there will be no change at all in the thermal conductivity of a gas or air because we are changing only this temperature, surface temperature. That's it, not the whole temperature.
Okay, sir.
If you change, if you reduce this T infinity by 500, in that case, there will be some difference in the properties of a air. Or even if you increase by 2000 Kelvin, there will be uh, some difference between a fluid property because in that case, the fluid property around yeah, fluid property around this body will get changed. But if you increase or decrease the surface temperature, there might be some change very near to the surface, but not around this body. So the fluid property around this body will be constant.
Okay, sir.
Is it clear?
Yes, sir.
Yeah. So let's move to next part. So in the next part, it is says that determine the heat flux at the same dimensionless location for a similar turbine blade having a chord length of L 80 mm when the blade operates in an air fluid. So we have the same in stream temperature and the velocity is 80. So velocity get reduced by half. So earlier it was 160, now it is 80 meter per second, and length become 80 mm. Earlier it was 40 mm. So in that case, we can use a similar expression, equation 1. So we need to check if the Reynolds number is changing or not. And it is given that we need to determine the heat transfer at the same point. For a similar turbine, at the same dimensionless location. So my X star is not changing here. And to determine if the Reynolds number is changing, we define the Reynolds number as V L by mu. So my V is becoming half and my length is becoming double. So my Reynolds number will also is not changing. So my Reynolds number is not changing. It is equal to the previous cases. So my X Reynolds number.
This Reynolds number that I think density is missing. You should have, otherwise you should have written kinematic viscosity nu.
Yeah. So I found. Yeah. So in that case, even the Reynolds number is unchanged. So my X star Reynolds number and Prandtl number is same, and we need to determine if my heat transfer coefficient is changing or not. So my Nusselt number is same. And my new heat transfer can be.
Suppose that there would have been any change in Reynolds number,
then my Nusselt number will not be equal to each other. In that case, in that case, we need to use the Nusselt number, which is a function of space, Reynolds number, and Prandtl number. Like you may have seen the Nusselt number expression in terms of some constant, Reynolds number to the power 0.8 and Prandtl number to the power 1/3. In that case, you need to use this equation, and you need to equate this equation to the let me say this is 1 and this is 2. So you need to equate these two equations in order to find the variables or the Nusselt number itself. Because your Reynolds number is not changed, so it will be different in both the cases. So you need to define a Nusselt number in terms of these variables to find the modified Nusselt number. But since these Reynolds number, Prandtl number, and X star is same, you can just write the Nusselt number in terms of heat transfer coefficient and thermal conductivity, and you can check whether these properties are different or not. Because the other properties are already same, Reynolds number and so on.
But sir, this Nusselt number that C raised to Reynolds number is to power 0.8, Prandtl number is to power 1/3. These are general equations, or these pertain to your previous numerical?
No. These are not the general equations. So this expression valid for the flat plate laminar flow. For the turbulent flow, it becomes different. So this power become different. And for the complicated geometry, it is the expression will become very complicated. So if let's say your Reynolds number is it is changing, and the Nusselt number is also changing with respect to Reynolds, Prandtl, and X star, then the quotient would have defined the correct expression for the Nusselt number. So we will solve such problems later on in this class, where we have given the Nusselt number in the form of Reynolds number and Prandtl number. We will just use the same Reynolds number expression to find the heat transfer coefficient and heat transfer ultimately.
But sir, here we don't know whether the flow is laminar or turbulent.
Yeah, so we don't have any information about the boundary layer in this flow. So we just have a uniform flow. That's it. So no description about the boundary layer is given.
I think then there is no need to check whether the Reynolds number, there is any change in Reynolds number. I think then there is no need to check because we don't have any criteria to further proceed if the Reynolds number changes.
Yeah, we don't need to change, but I'm saying like if the Reynolds number is unchanged, then we cannot follow this procedure. The simple procedure, we need to define the Nusselt number in terms of Reynolds number. So there will be expression of a Nusselt number in terms of Reynolds and other non-dimensional parameters. We need to use that Nusselt number then to find the modified Nusselt number or heat transfer coefficient.
Okay, sir.
So here we can define the modified heat transfer coefficient as H1 and L1 by L2. And let so this is my previous case, and I can define H1 from my previous case itself because these are not known quantities. So my H2 will be L1 by L2, and my previous heat flux is 95, 10 to the power 3, 800 minus 1150. L1 was 40 by 80. So this is my H2. For Q2, I can just put my H2 expression here. By 80 multiplied by 800 minus 1150. So I can just cancel these things. 2. So my Q2 will be just 95 by 2, 10 to the power 3, which is 47.5, 10 to the power 3 watt per meter square. So in this question, there is a change in the length of the object and the change in the velocity as well. And we found that we equate the Reynolds number, and we found that the Reynolds number is not changing. That means the Nusselt number is independent of Reynolds number, Prandtl number, and the non-dimensional length x naught. Now, since it is independent of this, we can just use the simpler Nusselt number relation in terms of heat transfer coefficient and thermal conductivity. Since the thermal conductivity is a constant with temperature, we can easily find the modified heat transfer coefficient using the previous data. And once we get the modified heat transfer coefficient, we will get the modified heat transfer, which is just a half of the previous case, 47.5, 10 to the power 3. So, any doubt?
No, sir.
Okay. So let's move to the next question. So this is a similar question. So here the experimental measurement of convection heat transfer coefficient for a square bar in cross flow yielded the following values. We have H1 when velocity is 20 meter per second and H2 when velocity is 15 meter per second. And we have given the Nusselt number in terms of Reynolds number and Prandtl number. And we need to find that What will be the convection heat transfer coefficient for a similar bar with L 1 meter and velocity 15 meter per second? So here we have given the Nusselt number in terms of C, which means that HL by K proportional to RN PRN. I can write the Reynolds number in terms of VL by nu. So my HL, so my thermal conductivity is, I'm assuming as a constant. So my HL will be proportional to VLM. So I'm not changing my Prandtl number as well. So my HL will proportional to VL to the power m here. So we need to find m here. So we have given data for V1 and V2. So we can use this data to find m. So my H1 is 50. So my L is 0.5 and H2 is 40. Yeah. V1 is 20. This is my M, so I can cross this. So it is just 5 by 4. 4 by 3 m. So on just calculating this, we will get m as 0.782. So this is my m. So the first part says that what will be the convection heat transfer coefficient when L is 1 meter and velocity is 15 meter per second. So we can use the same relation here. Let's say I have this HL, my H1L1, okay, V1L1, 0.782. H1L1. So my H is unknown when my length is 1 meter, I think. Yeah. So H is to be unknown quantity and H1 is my previous quantity. And it is 50. My previous length is L1, 0.5. And my new length is 1. And my velocity is 15. New velocity is 15. New length is 1 and my previous velocity V1 is 20 and previous length is 0.5. So after solving this expression, my modified H will be 34.3 watt per meter square Kelvin. So for the next part, we need to find the same heat transfer coefficient but with velocities is now changed to 30 meter per second. So same we need we will be using the same expression here. So this is my previous length, my new length is 1, and now the velocity changed to 30 and my length remains 1. Previous length is 0.5. So in that case my modified heat transfer coefficient is 59 watt per meter square Kelvin. So here in a question we have given a two condition. For two different velocity we have given two different heat transfer coefficient, and it says that let's you change the length and velocity, then how the heat transfer coefficient will get changed. And we have given some Nusselt number in terms of Reynolds number and Prandtl number. So we need to define the. So when we expand the Nusselt number and the Reynolds number, we got the heat transfer coefficient in terms of velocity and length as a function of velocity and length. So we define some specific relation, and from that relation we found which is given in terms of m also. We found m by using the data which is given in question. So two conditions are given, and these conditions are helpful to determine m. Now once we got the m, which is some constant, we use the same relation of heat transfer coefficient as a function of velocity and length to determine the modified heat transfer coefficient. So it doesn't matter how you change the velocity and length, whatever the change you have, you just plug into the expression to find the modified heat transfer coefficient. So any issue in this question?
No, sir.
Okay, so let's move to the next question. So the experiment result for heat transfer over a flat plate with an extremely rough surface were found to be correlated by Nusselt number, which is given in terms of Reynolds and Prandtl number, where NUX is a local value of Nusselt number at a position x measured from the leading edge of the plate. And we need to find the heat transfer coefficient, average heat transfer coefficient. So we can write down the Nusselt number as Hx 0.9, Prandtl number to the power 1/3, and I can then define Hx as 0.04 k 1 by x Reynolds number 0.9 and Prandtl number 1/3. So I can further expand my Reynolds number because my Reynolds number is a function of x, which is v by mu 0.9 x 0.9 by x 1/3. Now I can just collect all the constant. Let's say I collect Prandtl number, thermal conductivity, and hold this quantity. I will call this as C1. It's 0.1 minus 0.1. So this is my local heat transfer coefficient, C1, h to the power 0.1, whereas C1 is 0.04 k Prandtl 1/3. The velocity and kinematic viscosity ratio to the power 0.9. So now this is my local heat transfer coefficient, and now it is clear how we can find the average heat transfer coefficient. We just need to integrate it. dx. So on integrating it, we can have c1 x dx, c1. This will become dx, which is now on integration will be x minus 0.1 to 0. It will be some, so I'm absorbing minus sign into c1, so it will be 0.1. So this is my average heat transfer coefficient. Is it correct?
If you are writing this, then I think value of the C1 you should change that. C2 should, because 0.110 will be coming, 10 multiplied by C1. And so can we take that 1 over x into the integration sign and then we can integrate? Can we do this?
What? Sorry? What?
Like 1 over x you have written here. Average heat transfer coefficient is 1 over x.
Here. Yeah.
So when you are integrating, so this x you are taking inside the integration sign. Can we do this?
So here x is a variable, so that's why I took it to the inside. If I have a defined length L, let's say L, in that case it should be outside, and I can define my limit from 0 to L.
No, but in case of L it is constant. Whether you take it inside or out, you keep it outside, that won't matter. But here this x is variable. So can we take this inside the integration sign and then we should integrate it? Or
I think it is yeah. So the confusion happened due to the lousy notation, I think. So let me define this x bar, and this is my x bar. Yeah. So my x bar is constant now. So I can just need to integrate the inner part here. So now if I integrate it, I will get C1 x bar x 0.9 and it will be C1.9 x. So it is x bar now. If I include the limit, it will be x bar. So it will be now 0.1. So this is my 0.9. I can write as 1.1 C1. So this is my average heat transfer coefficient, and my local heat transfer coefficient was C1 x 10 x to the power minus 0.1. So I can write this as 1.1 times my local heat transfer coefficient. So my ratio of average to local heat transfer coefficient is 1.1. So yeah, so we have solved plenty of problems like this. So we have given the Nusselt number and we can able to deduce. So we have given a local Nusselt number. So therefore, we can able to deduce the local heat transfer coefficient, which is a function of x, and then we use the integration to find the average heat transfer coefficient. So yeah, any doubt in this? So we can move forward. So in this question,
So, sir, in this previous question, we should not take x inside before integration. Is it clear?
yeah,
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 yeah.
so, yeah, yeah.
Yeah.
So
Okay.
we should take x outside because to derive this relation we should use this. Let's say my temperature difference is this, and dA. This is my temperature difference. So it will be cancelled, and this will come outside the integral, which is 1 by L Hx dA. So this is the form of integral or the average heat transfer coefficient. So this L is always should be a constant. So x should be the constant here. So it should be always outside the integral.
Okay.
So in the next question, we have a laminar for a laminar boundary layer flow over a flat plate with air at 20 degrees Celsius and 1 atm. The thermal boundary layer thickness delta T is approximately 13% larger than the velocity boundary layer thickness delta, and we need to determine the ratio of both the boundary layer thickness if the fluid is ethylene glycol under the same flow condition. So first we have a air on a flat plate, and there is a boundary layer due to the air, and it is defined that for air we need for air the thermal boundary layer is 13% larger. Using that, we need to determine the same ratio of boundary layer, thermal boundary layer, and hydrodynamic boundary layer for the different fluid, which is ethylene glycol. So for air, let me define the properties. Prandtl number is 0.709 at temperature 293 Kelvin and 1 atm pressure. And for ethylene glycol, my Prandtl number is, let's say, 211 at temperature 293 Kelvin. So I can define the Prandtl number as del by del T for air, and we need to define N here. So the Prandtl number for the air is, and from the question, my thermal boundary layer is 13% more. So using this relation, I can define N, which is 0.355. And then I can use the same relation. I got the N, and I can use the same relation to define the boundary layer thickness ratio. So for ethylene glycol, my Prandtl number is 211. And my ratio of boundary hydrodynamic and thermal boundary layer will be, just solving this, will be 6.69. So this is a straightforward question, provided that we know the properties of a fluid at a certain temperature. So once we get the Prandtl number, so for the Prandtl number, it is either always given in the question, or we just need to use the handbook to determine the Prandtl number of any fluid at a certain temperature and the pressure. So once we get the Prandtl number, we just use the available data in the question to determine N, and once we get N, use the same relation to get the uh, information about thermal or hydrodynamic boundary layer. So, any doubt in this question?
From where we have got this value of Prandtl number 211?
So, usually in an exam scenario, it will be always given, Prandtl number will always be given, but we can take this value from the handbook, from where there is a variation of Prandtl number with respect to temperature. So for different kinds of a fluid, we can just define the Prandtl number. So usually in the textbook, for
211 is not given in the numerical.
no. In numerical, they have not mentioned any properties of fluid. So usually in the example problems, they don't mention the Prandtl number. So we need to take that from the handbook or some available data. Otherwise, in an exam, it is usually given. Prandtl number is directly given in the question.
Okay, sorry.
Yeah, so the main concept behind this question is to use the available data to find the constant like n, m, we found m in the previous one. And once we get the exponent on this constant, we can use the same relation to define the modified property or just a ratio, whatever it is asked in the question. So let's move to the next question. So in this question, we have a force here at temperature 25 degrees Celsius and velocity is 10 meter per second is used to cool the electronic element on a circuit board. We are given the dimension of a chip 4 by 4 mm located 120 mm from the leading edge of the board. Experiments have revealed that flow over a board is disturbed by the elements and the convection heat transfer is correlated by Nusselt number expression, which is a function of Reynolds number and Prandtl number. So again here in this question we can just directly use the Prandtl number and the properties of the flow from the handbook, and we need to determine the surface temperature if the dissipation is given as 30 milliwatt. So let me write the properties of the fluid here. So the Prandtl number of it is 0.703 and the thermal conductivity is 26.9 10 to the power minus 3. Kinematic viscosity is 16.69 10 to the power minus 6. And in the question is given that there is a energy dissipation is happening, and over the plate there is a chip flow.
I think, sir, this kinematic viscosity, it should be meter square per second, not m raised to power minus.
Yeah, it is meter. Yeah, sorry.
Okay.
So there will be some dissipation and there will be some heat convection due to the air which is flowing over the chip. So from the energy balance, I can just write my heat generation is equal to the heat convection due to air. So from Newton's...
Isn't it a constant surface heat flux situation?
Constant heat flux situation.
Constant surface heat flux.
No, so there is a heat generation within the chip. So whatever heat generation is there, it is removed by the flow of air at the surface.
No, but that heat removal is constant. That rate is there, 30 megawatt.
Yeah,
milliwatt.
yeah,
So that flux is constant, it means.
yeah. Flux is constant with respect to time. So there is a constant removal of heat, which is 30 milliwatt by the year. So yeah, so you can just say that there is a heat transfer of a 30 milliwatt
Okay.
and area is constant. So yeah, there is a constant heat flux. So from the Newton's law of cooling, I can write as Ts to T infinity. So I need to determine Ts, surface temperature. So I can write this as like this. So we need to determine the heat transfer coefficient, and we have given the Nusselt number. Can write this as checks K. So X is given as 120 mm. So that is the total length. And my Reynolds number will be written as VL by mu. So I just need to plug the value to find the heat transfer coefficient. So let me just plug all the values. So this is my thermal conductivity, and my length is given as 120 mm. Velocity is 10, and my kinematic viscosity is 16.69, 10 to the power 6, and my Prandtl number is for the gas is 0.703. So just equating this expression, we will get our heat transfer coefficient as 107 watt per meter square Kelvin, and then we can use equation 1. To determine the surface temperature. So this is my energy generation, and my heat transfer coefficient is 107, and my area will be 4 mm by 4 mm. So just after calculation, just calculating this expression, the surface temperature will be 42.5 degrees Celsius. So in this question, we are given that there is a constant generation of energy which will be carried away by the air at the surface, and we have given the Nusselt number. So to determine the surface temperature, we just use a simple energy balance and the Newton's law of cooling, but we need heat transfer coefficient, which is unknown, and we have given the Nusselt number expression. So from the Nusselt number expression, we can found the heat transfer coefficient, and once we got the heat transfer coefficient, we can find either the heat flux or the surface temperature, whatever is unknown. So main objective in the convection problem is to always find the heat transfer coefficient from the Nusselt number, and then to find heat transfer or the temperature, whatever is unknown quantities. So any doubt in this question?
Sir, can you show the that schematic, that diagram?
Yeah. So this is the cross section over which the air is flowing. And there will be a generation of heat which will be balanced by convection heat transfer. So any doubt?
Okay, sir. Clear.
So let's move to the next question. So this from this question we will be using the Chilton Colburn analogy, which actually defines the relation between the skin drag coefficient and the other non-dimensional number like Prandtl number or Staten Reynolds number and so on. So we have given a thin flat plate which is 0.2 by 0.2 on side, parallel to the atmospheric air stream, having a velocity of 40 meter per second. And the air is at a temperature of 20 degrees Celsius, while the plate is maintained at temperature Ts 120 degrees Celsius. The airflow over top and bottom surfaces of the plate and measurement of the drag force reveals a value of 0.075 Newton. What is the rate of a heat transfer from both sides of the plate to the air? So we have given a plate here, and there is a inflow coming from the left hand side. My velocity of incoming air is 40 meter per second, and my temperature of air is 20 degrees Celsius. And yeah, my surface temperature is 120 degrees Celsius, and we need to define the heat transfer. So there will be an airflow at the top as well as in the bottom also. So there will be heat transfer from the top surface to air, and the same amount of heat transfer is from the bottom surface to air also. So from the Newton's law of cooling, I can define as, because there is a heat transfer from the upper part as well as from the bottom part. So I'm using the twice. And we need to find the heat transfer coefficient. And here we have given the drag force, and we have air. So we can use the Chilton Colburn analogy, which is, so we can use their expression. So here H is the heat transfer coefficient, and Cp is the specific rate, and Cf is the drag coefficient, and PR is the Prandtl number. So we know that for the gas, the Prandtl number is 0.7. So we have already solved a couple of problems with the Prandtl number 0.7. This is for gas. And let me define the properties for air. My density is 0.018 kg per meter cube, and my specific heat is 1000 approximately joule per kg Kelvin, and my kinematic viscosity is 20.22 10 to the power minus 6. So these are my properties of air. at temperature 70 degrees Celsius. So we have a heat transfer coefficient which is unknown, and the skin drag coefficient is also unknown here. So from the last week we used some fluid dynamics relation to define the skin drag coefficient. So we can also define the skin drag coefficient in terms of shear stress. So let me write the drag force expression. So my drag force will be Q infinity square and area. So my skin drag coefficient will be 2F area. And we already have given the drag force, which is 0.075 Newton. So we will use this relation here to define the heat transfer coefficient. So this is unknown here. So I can simplify this expression as 2, this will be cancelled. So it will be rho u infinity Cp. So this is my expression for the heat transfer coefficient, and we just need to plug the values. So Cf can be calculated from the above expression here, which is 0.075, density is 1.018, the velocity is given as 40, and my cross-sectional area is 0.2 by 0.2. So using this expression, my Cf will be 5.74 10 to the power minus 4. So I can use this Cf value here, 5.67 10 to the power minus 10 to the power minus 4. My specific heat is this, and my Prandtl number is 0.7. 2 by 3. So on just calculating this, my heat transfer coefficient will be 30 watt per meter square Kelvin, and then I just need to use the Newton's law of cooling here. So my surface temperature was 120, minus 20 is the airflow, and by solving this we will get the heat transfer 240 watt. So here we have given a plate, and this question says there is a heat transfer from the upper side of the plate as well as from the lower side of the plate also. So to find the heat transfer, we all know that we need to use the Newton's law of cooling here. But the major task is to find the heat transfer coefficient, and in the question it is given that the drag force is 0.075 and we have an air here. So we use the Chilton Colburn analogy and we equate the drag force coefficient with the heat transfer coefficient. Since the drag force coefficient is also not given, we use the relation from the fluid dynamics, drag force relation, to find the skin drag coefficient or the drag force coefficient. So we already know the drag force, we already know these parameters, and from this, using this, we found the drag force coefficient. Once we get this, we can relate it to heat transfer coefficient to find the heat transfer coefficient, and then we can easily use the Newton's law of cooling, Newton's law rule, to find the heat transfer rate by convection. So any doubt? So you can use this Chilton Colburn analogy only for the air. In case we are given any uh, different liquid, I think you can use the Reynolds analogy only for air. Chilton Colburn analogy can be valid up to candle number 60. So yeah, it's nothing major. So any doubt?
So actually, in most of the problems of that is even Colburn equation, Caesar rate equation,
Yeah.
there the flow is only on flat plate on the one side. But here we are considering flow on both the sides.
Here
So
it
won't there be any change in the boundary layer? And when there is a change in the boundary layer, then all properties will change.
So first, there is no information of the boundary layers. So we have only a uniform flow. That's it, which is passing over the flat plate. And so we don't have any information of boundary layer. But yes, if we have a boundary layer, which is on both sides, then there will be a change in the magnitude of the heat transfer coefficient, and there may be a change in the properties also due to the change in the temperature.
But this Chilton-Colburn equation, I think that equation when there is flow over the flat plate, not on the both sides. So can we apply this equation when there's flow on both sides?
No. So when you have given any information about the drag coefficient or the drag force, then only you should apply this relation, because otherwise you are actually relating a new quantity, which is a drag force coefficient, to some heat transfer coefficient. So this is the unknown quantity in the question, and you are introducing some another additional unknown quantity. So in case you have given some shear stress or a drag force, or the stress which is causing by air when it is hitting the surface, which is the shear stress, which is due to this drag force itself. In that case only you can use this relation, because you have given the drag force information. You can find the drag force coefficient, and then from here you can find the heat transfer coefficient. So otherwise, when you have no information about the drag force or the drag force coefficient and all, you should avoid using this method. You should avoid this method. So this method only is there when there is a relation between a drag force coefficient and the heat transfer coefficient. Yeah, that's
Okay, sir.
okay. So let's solve something similar problem again. So here we have an atmospheric air is in a parallel flow over a flat heater surface that is to be maintained at a temperature 140 degrees Celsius. We have given a free stream variables like velocity and temperature. The heater surface area is 0.25 meters square, and the airflow is known to induce the drag force 0.25 Newton on the heater. What is the electrical power? So this is the same question. So we need we will be using the same procedure here. So we need to find the heat transfer, which can be given by Newton's law of cooling. And we know that H is unknown. So we will be using the same relation. And we have given the drag force also, which is 0.25 Newton. And just by putting the value, so the densities I'm considering the same, say 1, and U infinity is 15 square, and the area is 0.25, and I will get my drag force coefficient as 8.93 10 to the power minus 3, and then I can use the same thing to find the heat transfer coefficient, which is CF by 2. So the Prandtl number for the gas is same, 0.7, and then my heat transfer coefficient will be so we can just calculate here, and we will get the heat transfer coefficient is 85, and then my total heat transfer is 85 multiplied by area. My surface temperature is 140. This is my air temperature. So this is Ts, T infinity, area, and H. So just calculating, after calculation we will get 2.6 is 10 to the power 3 watt. So the same question, we just have a flow over a flat plate, and we use the same Newton's law of cooling, and we use the same method. We found first drag force coefficient, and then we found the heat transfer coefficient, and then the total heat transfer.
So again, that when the flow is on both sides, then we are using the same equation. When it is only
No. It is not. No. If the flow is on the both side, you just need to change the magnitude of the heat transfer, because there will be a heat transfer from the top to air as well as from the bottom to air. That's all. We are not using this method because of the direction, because of the multiplicity of the flow, that the heat transfer is either on both sides or is on the one side. We are using this relation because we are given the drag force. That means there will be heat transfer coefficient is a function of a drag force, because it is experiencing some drag, and it will from the drag force, the magnitude of the drag force can be determined from the drag force coefficient. And from the Chilton-Colburn analogy, we can write the drag force coefficient in terms of a heat transfer coefficient. That's the only reason we are using this method. So if you are given a drag force of the shear stress, or directly the drag force coefficient, then only you have to use this method. That's it. Even if you have a, let's say, flow, let's say you have a plate here, and there is a flow above the plate as well as below the plate. There will be a heat transfer from top to air as well as from bottom to air. And you have given some Nusselt number relation as a function of Reynolds number and Prandtl number. So in that case also, you just found the heat transfer coefficient from the Nusselt number, and you have to use the Newton's law of cooling as, because there is a twice heat transfer. There is a heat transfer from here Q, and there is a heat transfer from here Q. So basically you are doing Q plus Q, which is 2HA Ts minus T infinity, and this is your total heat transfer. That's all. So we are just determining the different ways of calculating the heat transfer coefficient. So if you have given the Reynolds number or the Nusselt number expression, you just use that. If you have given the drag force information, something about drag, then you can use the Chilton-Colburn analogy to determine the heat transfer coefficient. Once you get the heat transfer coefficient, you just use the Newton's law of cooling. Now here 2 is coming because the heat transfer is taking place from bottom surface as well as from the top surface. So here it is Q and here it is Q. So basically you are doubling the heat transfer.
So please let me note down the relation of.
Yeah. Anyway, you can found in any book. It is given.
Okay, let me note down, sir. Okay, sir.
Yeah. So the last question is also very same question. So on this one, the 12th number, yeah. So this is the same question. So here, instead of a drag force, we have given the shear stress, and we can just find the drag force from the shear stress relation. So shear stress is just a force per unit area. So once you get this drag force, you can just then find the drag force coefficient and then heat transfer coefficient and then total heat transfer and all. So you can try this question out. So I will upload this PDF into the Google Drive. So from there you can just try the question. The method is all same, or you can use the properties of air. Like I can just write the properties of air here. So you can use the density as 1.161 kg per meter cube. Prandtl number 0.707. Specific heat is 1007 joule per kg Kelvin. Yeah, so these are the properties you need. And just for practice, the method is same. You can use the same Chilton Colburn Analogy, and procedure is same. And we need to define the I think the average heat transfer. Yeah, we need to define the heat transfer rate. So for practice, you can just solve this question by yourself. So let's move to the next question. So we have for a flow over a flat plate. Over a flat plate with an extremely rough surface, conduction heat transfer effect are known to be correlated. Okay, we have given some expression there. So I think so. Let's solve this question in the next class because I have not written the expression here. So I will start the next class from this question. I will get the relation, and that relation will be useful to determine the heat transfer coefficient. So yeah, that's it for today. So any doubt until now? I mean, any doubt in any question for today?
No, sir. That only my issue is that
Video, right?
video. I think
Yeah.
that video.
Yes, I will look into that. I will.
Okay
If
then.
it change, I will just inform you.
Yeah. Okay then. Okay. Thank you.
Okay. Yeah, Anil, you have any question? Okay.